Hello everyone, my name is Genaro Zambrano, and I'm going to be exploring the effects of tornadoes using fluid dynamics. Tornadoes are known for being incredibly destructive, and for one of the reasons is the pressure differences that are on the inside and the outside of the core. Today we're going to be using two tools from fluid dynamics, Bernoulli's equation and cyclotropic balance, in order to estimate how the pressure drop happens. By the end, you'll understand the physics behind tornado density and see an example calculation using realistic tornado winds. So, when a tornado forms, air spirals inward and accelerates dramatically. As it does, the pressure at the core can drop by a few dozens of kPa in strong tornadoes. This pressure drop is a major contributor to damage. It's what causes the windows to blow out, the roofs to rip off the houses, and even collapsed warehouses and similar big structures. Despite the variables related to the tornado, like humidity, debris, and vertical motion, we can still get a good estimation. So to begin, I want to explain the first principle of Bernoulli's equation. It connects pressure and velocity in a streamline where friction is negligible. For the purposes of the topic, we can consider it a spiraling vortex. So, the normal equation considers pressure versus the velocity and the height, the potential energy section of it, compared to two different states. We can ignore the second state and ignore the potential energy of it and derive it down to, just as the simple equation here, pressure difference is equal to 1/2 density times velocity squared. Now, it's just an estimation though. Cyclotropic gives us a better instance of this. In most atmospheric flows, like hurricanes or jet streams, the Coriolis effect matters. But for tornado cores that are so small and rotate so fast, the Coriolis effect becomes negligible. This allows us to use something called cyclotropic balance, which states that the inward pressure gradient force balances the outward centrifugal force of rotating air. The equation is 1/density times the pressure gradient equals the angular velocity squared over the radius. This equation describes rotation held together by pressure. The faster the air spins, the larger the pressure difference needed to keep it rotating in a tight circle. When we integrate this relationship for a simple vortex, we get a similar result. The difference in pressure is equal to 1/2 density times velocity squared. So both Bernoulli and cyclotropic balance lead us to the same prediction, but cyclotropic balance gives us the physical reason the pressure must drop. The air needs an inward force to stay in a curved path. Okay, now, let's apply this for a real tornado. El Reno was a devastating tornado that landed in Oklahoma back in 2013. It was an EF5 tornado with wind speeds up to 150 meters per second. If you consider the air density at the ground to be 1.2 kilograms per cubic meter, what will the pressure difference equate to? Well, if we plug in these values into the formula we just derived, we'll get 13,500 pascals, or 13.5 kilopascals. That's a big difference, but it's hard to illustrate that with just a strange pressure unit at the end. So we'll show the true upward force. We can take the median roof sides in America to be 157 square meters. Now we plug it into the force equation. That brings our force to over 2 million newtons of force. That's over 238 tons of force. That's enough to lift the Statue of Liberty off its pedestal. Now, of course we calculated a crazy strong tornado, but just because they are rare doesn't mean we shouldn't still plan for them. That's exactly what engineers and meteorologists do. They design structures for tornado-prone areas to keep you safe and use these to interpret tornado damage patterns. Now to wrap up, I want to go back over some key points. We use Bernoulli's equation and cyclotropic balance to gain insight into why tornado cores experience such low pressure. While tornadoes are extremely complex, these simplified models still capture the core physics behind the pressure drop. Remember, faster rotation creates higher pressure drops. You can calculate this using the following equation. Even an EF1 tornado can still trip the roofing off your house at just a 5 kPa difference, but they can get up to 30 kPa. Try this at home for a tornado and leave it in the comment section. Thanks for watching. Peace.